Welcome all. In these lectures, we will learn about functions of complex variables. Now, functions that are complex are very often used in physics in topics such as electromagnetism and quantum mechanics. We've seen umpteen examples of functions that are complex. By complex functions, we mean functions that have a real part and an imaginary part. The function that I have written is one such example. It is a function of a position vector r, and it is found to have a real part which I have represented using f1r and an imaginary part which I have written using the symbol f2r. As I said in the beginning, such functions are very often found, for instance, when we try to represent an electromagnetic wave in electromagnetism. We could recollect that if I want to represent the electric field due to a moving electromagnetic wave, I would very often write it as a function of position as well as time, and it is very often written in a form in which it has a real part and an imaginary part. Another occasion where we use complex functions is in quantum mechanics, where we try to describe the state of a system by writing its wave function. The wave function that we write as a function of position r and time t is also a complex function which has a real part, which I will write using psi1 rt, and an imaginary part. There are several other examples that we can easily find if we span through all various different areas of physics. The goal of these set of lectures is to study complex functions, not of arbitrary variables, but of complex variables. And most of us are familiar with the idea of complex variables. It's basically a variable that has a real part and an imaginary part, very often denoted using the letter W, Z or W, and the real part of which is denoted using X, and the imaginary part of it is represented using the variable Y. This is a very useful way of representing points on a plane. So, it is clear that whenever we are studying functions that have specific values for each point on a plane, complex variables are going to be very useful to study such functions. It is also worth mention that the place where we make use of functions of complex variables in physics are not so often when we study points on a plane, but in cases where we study points on a line itself. And such possibilities, the possibility to use complex variables even beyond situations where we have where we are looking at points on a complex plane or a sheet, is because of certain special properties that such complex plane and functions on the complex plane have. So our goal will be to understand in the brief time that we have as much possible about functions of complex variables as possible. Okay. Let us now begin the lectures by briefly recapitulating our knowledge about complex variables that we may have acquired right from our schools or during our undergraduate studies. Okay. As I mentioned earlier, a very common way of representing a complex variable is by writing it as a real part plus an imaginary part. This way of writing a complex variable can be represented on an xy plane that we are familiar with by identifying the real part with the x axis and the imaginary part with the y axis. So, for instance, if I am looking at a point with its real part given by x and an imaginary part given by y as given here, then I am referring to that point with its value on the x axis being x and its value along the y axis being y. Now this way of representing a complex variable, or this way of identifying a point on a plane, is very familiar to us because we have been doing this since the time we learned about Cartesian coordinates. So the way I write a complex variable in this fashion can be readily identified or readily called the Cartesian way or Cartesian form of representing a complex variable. Now, as with points on a plane, this is not the only way of locating its coordinate on the plane. There are other means that we are familiar with by choosing a different coordinate system. One very commonly used example is the polar coordinate system. If you recollect what polar coordinate system does, it is to assign that point a coordinate by finding the distance to that point from the origin, calling it r, and then measuring the angular distance of that line from the x axis and calling it theta. given r and theta, again we can identify that point by noting that the x coordinate of that point can be represented as r times cos theta, and the y coordinate as r times sin theta. We could write the same thing as r times cos theta plus I sin theta together. That makes up what is well known to be exponential of I times theta. So, this gives us another way of writing a complex variable z, that is by saying what its distance from the origin is and measuring at what angle that point is from the real axis. Okay. This number is often called the modulus of the complex number z, while theta is called the angle of z, or sometimes also called argument of z. It is important to note that in either of these forms, the coordinates that we use are in either of these forms, all the coordinates that we use are all real numbers. For instance, in the Cartesian way of writing a complex number, the real part is represented using x, where x is a real number. The imaginary part of it is y, and y is also a real number. Coming to the polar form, r is the modulus of z, which actually gives us the distance from origin to that point. That is a real number. In addition, theta is the angular distance of that line joining the point to the origin from the real axis, and that is also a real number. So, in all of these forms, we are writing a complex number in terms of real numbers, and we need two real numbers to write that complex number. Recall that I that we use is square root of minus 1. Having seen this, it is important to understand the notion of conjugate of a complex number, of the complex number z. The definition of a conjugate of a complex number expressed in the Cartesian form is, it's denoted using z bar, and it is equal to x minus I1, wherein we retain the sign of the real part while changing the sign of the imaginary part. The complex conjugate of z, denoted using z bar, also represent a point on the complex plane. For the z which we have on this complex plane, it is easy to identify where z bar is. It is that point which have the same real part, while has an imaginary part which is along the negative y axis. it is that point, x comma minus y. Now, if we look at these 2 points, or if you look at the 2 lines joining the point x y to 0 and the point x minus y to 0, it is clear that they together provide a convenient coordinate system. As we know, on a plane, we always require 2 coordinate axes to represent a point. This is because you need 2 coordinates to identify a point on a plane. In Cartesian form, it is x, y, where we choose x and y axis as 2 mutually perpendicular axes, 2 mutually perpendicular lines as the 2 axes. In polar form, we choose the distance to the point as 1 coordinate r and the angular separation between that line and the real axis as the second coordinate. Now, if we use z and z bar as 2 coordinates, we could again represent any point on the complex plane in terms of these, in terms of only these. It might look a little bizarre or unnatural that we use a coordinate z and its own complex conjugate, which can be found completely from that coordinate, that we can use 2 such coordinates to represent a point or represent any point on the plane. Let me restate it. Okay. It might sound a little unnatural that we use z and z bar to represent any point on the complex plane. After all, when we look at z bar, we find that we can identify z bar provided we know z. However, that is not the case if I give you simply r. By simply giving r, it is not clear at what angle the line joining that point to the origin is from the real axis. For instance, another point which is at the same distance from origin could have a different value of theta. So, it is clear that it is not sufficient for me to give r alone to find theta. And the very same thing is true with the Cartesian form also. If I simply give you the real part of a complex variable, a complex number, it is not the imaginary part of the complex number is not automatically found. That has to be given separately. However, with z and z bar, it might look as if they are not independent, but this is not true, as can be seen readily if I erase the z axis and y axis. If you are not given the real axis and the imaginary axis, but given only the z axis and the z bar axis, it is now clear that knowing only z and z bar, it is not easy for us, or it is not possible for us to find z bar given only z. So, this way we can write down, recall that I is square root of -1 in whatever we do. Let us look at an example of a complex number. Let us take the example of a complex number z1 of the form square root 3 plus I. In here, I have expressed the complex number as a real part, as one having a real part and an imaginary part, from where we can directly read off its real part, which earlier I have represented using x, for this case, for the case of z1 to be x1 equal to root 3, and its imaginary part, which I denote using y1, as the coefficient of I, which is 1. The same can be represented using the polar form or inner polar form by finding out what r and theta are in terms of x and y. Now, in the expression stated earlier, I have provided the relation for the x, real part x, as well as the imaginary part y in terms of r and theta. If I want the inverse relation, which is to get r in terms of x and y, that is easily seen to be square root of x square plus y square, while theta is inverse tan of y over x. So, for the case of this complex number, we could easily find the polar form by substituting for x from here and y from here. We see that r1, the modulus of this complex number, happens to be x1 square plus y1 square under square root, which is 3 plus 1 equal to square root of 4, which is 2. And theta in this case works out to be inverse tan of 1 over root 3. Using these two, I could represent z1 also in the polar form as 2 e power I theta 1. Well, let me call this theta 1. Theta 1, where theta 1 is given in that form. With the introduction of complex variable z to represent a point, it is immediately clear that we could find another complex number, which I will denote z bar, by changing the sign of only the imaginary part of the complex number z. The complex number obtained this way out of z is called the conjugate of z. And on the complex, on this plane, xy plane, it is easy to identify the point represented by z bar. That should be the point which has the same real coordinate x, but the imaginary coordinate has changed sign. That means it must have the same x coordinate, but y coordinate must be negative of that of z. That is this point. Now, looking at the position vectors representing z and z bar, looking at the position vectors representing z and z bar, we could observe that these two position vectors can be used to introduce a new coordinate system for points on the plane. And what is that coordinate system? Let us identify a way of writing points on the complex plane in terms of two such variables, z and z bar. Let us choose some z, some concrete example of z and z bar to do this. Let us choose the example that we have chosen, square root 3 plus I to be z, or let's call it z1, and then z bar should be, or z1 bar should be naturally square root 3 minus I. Let us observe the following point, that if I identify any arbitrary point on the plane, instead of writing it in the Cartesian form as given here or in the polar form as given here, I could also write the same in terms of this point z1 and its complex conjugate z1 bar. Let us pick one arbitrary point, let us say let us choose a complex number z2 with the square root of 8 plus I into 5 over 2, some arbitrary point, and try to see that the same thing which now I have written in Cartesian form can also be represented in terms of, or can also be written in terms of z1 and z1 bar. Let us see how I do this. Now, having gotten the real part of this, which is x2, calling it x2, its value is square root 8, and its imaginary part, calling it y2, is 5 over 2. In order to write this complex number in terms of the complex number z1 and its conjugate z1 bar, let us note that x1, the real part of this complex number, can be easily seen to be z1 plus z1 bar over 2, and y1, the imaginary part of this complex number, is z1 minus z1 bar over, or I times y1, the imaginary part of the complex number is z1 minus z1 bar over 2. The value of x1 in this case is square root 3, and the value of I times y1 in this case happens to be 2I. Or I. Now, coming to this complex number z2, we could observe that this can be written as square root 8 times x1, or square root 3, in the case given it is square root 3 over square root 3. And I into 5 by 2 as I into 5 by 2, where I is the factor that is the imaginary part of Z1. Having written it in this form, now let us show that we could represent such an arbitrary complex number as A times Z1, where Z1 is the one that I have chosen earlier, namely square root of 3 plus I, plus where A is some real number, and B times Z1 bar, where B is another real number, times Z1 bar, where Z1 bar is the number that is conjugate of Z1 that I defined earlier. By substituting the forms of Z1 and Z1 bar here, we could observe that square root of 8 plus I times 5 over 2, which is what Z2 is, equal to A times Z1, which is square root 3 plus I, plus B times Z1 bar, which is square root 3 minus I, we could try to solve for A and B, and thus ensure that such a representation is possible. Now, how do I solve for A and B? Well, I could equate the real part on either side by writing the real part on the left hand side as square root 8 equal to the real part on the right hand side, which is square root 3 times A plus square root 3 times B. And the imaginary part as 5 over 2 on the left hand side to be equal to A into I, A from the first term and minus B from the second term. By solving for A on either side, we could see that A is going to be equal to square root 8 plus 5 into square root 3 over 2 whole divided by 2 root 3 . We could observe, we could find the value of A and B to be equal to square root 8 minus 5 over square root 3 over 2 over 2 times square root 3. So, having known what A and B are, we are now assured of the fact that a complex number Z2, which we have chosen arbitrarily, can be written in terms of Z1 and Z1 bar, where Z1 and Z1 bar were also chosen earlier in this form. So, this shows that I could write an arbitrarily chosen complex number Z2 always in terms of a complex number and its conjugate. Okay, this exercise gives us confidence in identifying Z, complex variable Z, and its complex conjugate variable Z bar as independent variables on a plane. This is quite natural because any two lines on a plane that are not collinear, we know such two lines can be used to provide a coordinate system for the points on that plane. So, it is clear that Z and Z bar fits the bill, and from now onwards we will represent a plane in which we intend to use Z and Z bar as the variables as a complex plane. We will henceforth refer to it as a complex plane. It is important now to find the relations of the earlier used coordinates, the Cartesian form x, y, and r, the polar form r and theta. It is important to find the relations of these coordinates with our complex variables z and z bar. That is easily done because it is easy to see from the form of z and z bar that we had earlier used, that x, the real part in the Cartesian form, is just the sum of z with z bar divided by 2, while y, the imaginary part, is z minus z bar over 2 times I. Coming to the polar form, the modulus r can now be easily identified with square root of z, with square root of the product of z with z bar, while theta can be identified with minus I over 2 of natural logarithm of z over z bar.